Hello.
Hello, hello, hello. Hello, hello, hello. Check, check. Hello, hello.
Can you like navigate into the slides? We'll check if everything. Yeah.
I don't see Ashu's. I see Ashu here on your laptop, but not there. Why is that happening?
Yeah. So can you switch off your video and switch on it once more? Yeah. Yeah.
How about now?
We can see you.
Okay,
Uh,
perfect.
so everything is fine. We'll start at 9:30, and I'll let you know.
Sounds good. I will mute myself for
Yeah.
now.
Can you
Okay.
hear me?
Wait a minute. Hello.
Hey, Ashu.
Hey, how are you?
I don't. I think I can't hear you because I had to put this on. Sorry.
Hello, sir.
Yeah. Hi. Hi.
Hello, hello.
Oh,
Yes.
I think I guess I get. Okay. Wait just a second. Yeah. So we'll start. Second. Having some echo issues, but we'll start at 9:30 sharp. So at around maybe 9:30ish, I'll introduce you. We don't have a full room yet. People are just still streaming in there having breakfast. So you're the first. You're the inaugural talk is for today. So, but we have a packed schedule, so we're going to start on time.
Yeah, yeah. I will be here. I'm now ready. Yeah.
Sounds
Thank you
good.
so much,
Thank you.
and good to see you again. Yeah.
Great to see you. Yeah, and you can feel free to sort of take a break now until we get started. It's about.
Yeah. I'm trying to figure out effects so that this whole
So,
fan doesn't show. I don't know whether it
it's all
has
good.
those blurring effect or not. People in
Sounds good.
session.
All right. Ashu, can you hear me?
Yeah. I can
Okay,
hear
we
you.
can hear you. See your slides. Are we ready to go?
Absolutely.
All right, wonderful. So, hello everyone, and welcome to the first keynote of this morning. It's my true pleasure to welcome Ashutosh Sabharwal, Department Chair and Professor at Rice University. It's a true pleasure to welcome him. He is a pillar of our field, works broadly in wireless communication and system design. He's known for his pivotal work in designing some of the early programmable radios as well as full duplex wireless systems. He's also one of the site leads of the NSF Power project that Professor Margaret Partnosi mentioned from the NSF mentioned yesterday. He has many accolades, Test of Time Awards. He's a fellow of the IEEE and among many other awards. So, without further ado, over to Ashu.
Thank you so much and appreciate the invitation. And first of all, apologies for not being there in person. Is one of my favorite places to be, but unfortunately, I couldn't make it in person this year. Um, so I will just dive into the topic for today, which is that wondering about what the next generation systems will be, and one of the areas where I think we all agree they are headed towards is being multifunction. And so the main vision, driving vision, is many of us are working on it. Is how can we do more than just sending bits over networks? And one of the interesting areas of discussion is, can we use electromagnetic propagation, which is being sent by these radios, to do more than send data? In fact, we would love to actually use it to see the world. And that's not something far fetched, because if you look at how we do vision, how do we do imaging, it is sending electromagnetic waves, which is often in the visible light spectrum, and then using cameras to actually image. So, what we like to do is somehow be able to do that using other parts of the spectrum, for example, the wireless parts of the spectrum. Um, so in communications, we are kind of used to this picture where we have a user which is sending data through a channel and being received at a base station. And this is a picture we understand very well. The whole conference, COMSNETS, is actually focused on these ideas. But in imaging, the idea would be that, can we use the transmitter as an illumination and receiver as our pixels to do image or learn about in the same environment in which we are communicating in? And imagine if you could do it, then, considering that the base stations are deployed at a very large scale, we could form images at city scale. Now, for example, if we could actually do high resolution imaging using these things in these bands, then perhaps we could actually form understanding of the whole environment at very large scales. Okay, so these are just a sample idea. These are not actual images from an experiment. So what we are working towards is what we call dual function wireless networks where there's communication going on. For example, the uplink user talking to the base station, and then the base station also using its resources for imaging the actual scenes. Now, I wanted to actually take a little bit of a detour how we ended up in this problem, and which is kind of just talk about this link, which is the full duplex link, and how we actually got there. So, um, I've been working in wireless for a while. So, like most careers, I also have a circuitous career which is still evolving. So started working on more algorithms and theory side, but ended up loved making building systems. So actually built this open source platform called Warp. Um, that led us to allow us to do full duplex experiment, which I will quickly mention, but also start working on with my colleagues on massive MIMO wireless, which is then became the basis for one of the power projects, which was mentioned earlier on. Um, so Warp, which was something built out of necessity, while software defined radios were not readily available to academics, so we actually built our own, mostly out of necessity, but then our colleagues really wanted it to, so we made it an open source project, spun it off as a company which produced the hardware, But more than the accessibility, it also naturally also led to change in the methodology of how we did research as a community. Um, that availability inspired my colleague Lin Zhong to actually use that platform to build a massive MIMO system and called Argos, which is some of the older versions are demonstrated here. These were built very early on, now a decade ago, and they were up to, we actually built systems which were up to nearly 100 antennas. Um, and on the full duplex side, this allowed us to actually investigate and understand how can we do simultaneous transmission and reception at the same time. And the challenge there was not a conceptual one, but a practical one, where you have a very large self interference. How can you actually suppress it so that you can get a weak uplink signal while you are transmitting to a downlink node? So that led to different self interference suppression ideas. Um, More importantly, we could demonstrate them on actual software defined radios. And around the same time in 2010, two papers came out, one from the Stanford group, one from our group, using these inexpensive software defined radios to actually demonstrate that practical full duplex is possible. Um, so fortunately, that was picked up by the industry. So first, it led for wireless. Of course, in wireless industry was looked at it, but in fact, by 2016, it became part of cable modem standards. So DOCSIS 4.0, which is a cable modem standard, is actually completely full duplex. Um, and then fortunately, 5G was coming around. 5G technologies which use massive MIMO um, required large number of antennas, which are actually best to operate in a time division duplex mode, and that became a great perfect opportunity for them to do full duplex. So we actually started researching around 2016 on how to build full duplex on massive MIMO. But in fact, that led to some more innovation where we actually eliminated most of the analog cancellation, again using our software-defined testbeds, and that we led us to a couple of nice papers which showed that one can actually build full duplex using half duplex radios by just sacrificing a few degrees of freedom. Fast forward a few years ago, Qualcomm and Samsung and other wireless companies actually announced product demonstrators to actually include these full duplex technologies in their base stations. So that's very exciting to kind of see things from lab all the way make it to products and standards. And that brings back me to the picture or the discussion point for today. Now that we have some confidence that we can build these links, full duplex links, they are also becoming the basis for us to think of these next generation networks, which, as I mentioned, will likely be a dual function network. That means they will send more than just bits, they will actually do more for us. So today I wanted to spend some time discussing potential foundations for this idea and the first step towards those foundations for this idea. Okay, so the opportunity lies, of course, that we have now hundreds of antennas in massive MIMO system. If you think of each antenna which sends signals and receives signals, you can think of them as an illumination mechanism and also a sensing mechanism. Think of them as pixels also, right? So we have hundreds of pixels on base stations these days. And equally importantly, there's a huge widespread coverage of these base stations worldwide. So these are the maps from 2G, 3G, 4G systems, and similarly, in a few years, 5G will penetrate most of the world. So we will have, imagine lots of pixels, base stations, and mobile handsets available for doing imaging. But the challenge is, even with hundreds of pixels, you actually have, compared to imaging at visible band, where you have megapixels cameras, these are still very small number of uh, available pixels. Plus, we want to use it not just for imaging, but also for communication. So questions are, what are the trade-offs in using wireless systems for both imaging and communication simultaneously. The other is multipath is commonplace in all wireless communication, and that's generally not very good for imaging because it really actually leads to what is called building shadows and shadowing. So that again begs the question, what is the impact of multipath and clutter on imaging resolution if you were to start using them wireless networks for imaging also. Okay, so we have some two recent papers which from one of my great current student Nishant, who has worked on theoretical aspects of it. And today I'm going to talk about one of his work to give a flavor of how these new foundations are emerging, and then hopefully inspire folks in the audience that there is just a lot of rich area of research to work on for us as a community. Um, okay, so uh, uh, m- today I'm going to talk about a trade-off between doing imaging and communication simultaneously in these multifunction networks. Okay. Um, so wanted to set it up, and so what I'm going to talk about is create a system model which actually will help us start understanding it, and talk about a trade-off which actually emerges naturally from this system model. Okay, so here is what we are after. Again, the simple picture: we have one device which is trying to communicate to a base station, and that base station is also doing imaging by transmitting and receiving its backscatter signal from the scene. Okay, and we have a certain number of antennas available throughout the system for transmit and receive, as indicated here. Um, Now, for imaging, we need a system model, and the model will be something we will borrow from the literature, which is to take the whole scene and divide it into voxels. Think of just kind of divided into small known areas, and each of those voxels will be represented by its location, which is of course fixed, um, and its reflectivity, how much of energy is reflected from that voxel. So if there is an actual object in that voxel, it will likely reflect some energy. If there is no object, it won't reflect any energy. So the amount of energy reflected will be give what is called reflectivity, and we want to estimate that per voxel. Okay, so that's how we'll represent the imaging scene. And if you actually write it out, you can write it out as the F's are the reflectivities here, and then you need certain amount of path losses of due to transmission, and then you have certain path delays, which is the transmission from transmitter to the voxel and from voxel to the receiver. Okay, you can actually simplify this thing um, and write it kind of neatly. We have two matrices. The left and the right matrices are path delay matrices, and then the diagonal matrix in the middle is actually the reflectivity which you're after. Okay, and X is is the illumination or the transmitted symbols for the imaging function. Okay. Similarly, we actually can write a communication models. This we actually quite familiar how to write. But here we will actually write a communication model in two parts, where we will say there is amount of uh, some energy which is transmitting through a, a communication channel, but also some part of that overlaps with what we want to image the scene with. So that's the overlap with the imaging field of view. So we will write the imaging field of view channels more explicitly, which will have reflectivities for this part, which is the overlap part, and then the non-overlap part will be just written as a traditional communication channel. Okay. So if you take these two parts, you actually now have sum total of the two functions. You have an imaging function part, and then the bottom one is a communication function part. Okay. So you actually get a full system model or signal model for this dual function network. Okay. Um, so then the next question is, how do we, what is the metric we will use to evaluate our performance? That's kind of really important here. So just to kind of remind ourselves, the goal of imaging is to estimate these unknown reflectivities. The goal of communication is to decode the unknown uplink data. So they are actually not equivalent in any way. Even if we write this clean model, rewrite everything, one is trying to estimate the reflectivities F, the other one is trying to decode the data. Okay, so um, it looks like a multiple access channel if you write it this way, where you're trying to recover this reflectivity communication tuple. However, there are different quantities. One, you're trying to estimate a continuous number, which is reflectivity. The other one, you're trying to decode discrete data. Um, so, but they consume the same resources of bandwidth and power. So we need a common metric to study this trade-off between operating these two functions. So if you look at the past work, there is actually a fair bit of past work which has done similar types of things, and they have adopted either capacity distortion trade-offs or Cramer bound rate trade-offs, um, and other metrics have been proposed. However, if you look at across all these metrics, many of them have no physical meaning. They're very hard to interpret, especially when it comes to the imaging task, and they are in different units. So it becomes the trade-off becomes very hard to actually study. That if I trade imaging in one unit, what does it mean in terms of communication rate? It's actually very difficult to actually use them for practical interpretation purposes. Fortunately, we actually don't have to invent new metric. Degrees of freedom is actually a possible unifying metric. It's physically meaningful, is actually unitless, and is jointly applicable. So the assertion is that we can do apples to apples comparison on resources used for imaging and for communications. Okay, so on for degrees of freedom, what does it mean for imaging purposes? So imagine we are trying to essentially estimate reflectivity, so essentially form an image of the scene. And if you have electromagnetic waves which are radiated and sampled using finite apertures, which is like small, finite size antennas, then degrees of freedom for imaging is how many signals can be resolved at the aperture. So that's the amount, the resolution, and that directly relates to resolution of how many voxels, unique voxels you can actually identify. Um, so in fact, you can actually mathematically write it if you have the signal model like that I talked about, and if you use linear reconstruction methods for this, then the degrees of freedom for imaging is just the rank of this linear reconstruction matrix, and it measures how close the two targets can be before they can till they can be resolved. Okay, and that directly relates to what is the notion of resolution in imaging. Communications degrees of freedom is well established, is the number of resolvable code words, and there is a well-known formula or methods to evaluate it, which is the rate you are can operate divided by the the degrees of freedom needed for the base instruction channel. Okay, so the key question then becomes, what is the degrees of freedom trade-off between imaging degrees of freedom on the y-axis and the communication degrees of freedom on the x-axis? Okay, and that's what I will give a first cut answer today. Okay, so first of all, will there be a trade-off? Going back to this simple picture, one should expect some trade-off actually. Now, what does imaging benefit? Imaging is amount of energy which can be reflected off an object and then reaches a sensor, pixels, right? So more energy which bounces off is actually better for imaging. And in fact, if you have direct line of sight between your illumination and sensing, it provides no imaging benefit. Okay, so in terms of imaging, more illumination across the scene is better. From in terms of communication, we really don't care how the energy travels. All we care is that the maximum amount of energy reaches the destination. Because if you look at the communication formula, is the maximum energy transfer is what is the main objective. Sometimes these two objectives can be aligned, and sometimes they can be at odds. So here is an example. If you actually had a strong direct line of sight channel, like the red arrow between the uplink user and the receiver, then communication would focus on sending most of the energy along this path and avoid path 2 where energy actually reflects off objects. Okay, so in this case path 1 is better for communication, but path 2 is actually better for imaging. So If this situation was reversed, that the reflective path was stronger, then actually in this case the two objectives align. Path 2 is actually better both for imaging and communications. Okay, so the overlap region in this case provides opportunity for aligning the two objectives. Okay, so what we'll do is we will simplify the parameter space for simpler formulas. So instead of writing square arrays or number of antennas, I'm just going to look at them as continuous apertures, which really simplifies some of the derivations and for degrees of freedom calculation. And they will be represented by these balls called with radius BTX, BRX, and CTX, which are the apertures for transmission and reception. Um, and then these different angles, omegas, represent how much of a scene we're trying to illuminate and what is the extent of communication channel which we're trying to use. Um, if with this notation, you can derive and what is the outer bound on degrees of freedom, where it the first inequality bounds the amount of degrees of freedom you have for imaging, second one bounds what you have for communication, and the third one bounds the sum of the two degrees of freedom. Okay. And what you can see is that there is actually potential gain from this overlap. Okay. So if we consider a zero overlap case, uh, where there is no overlap between the um, communication channel and the imaging scene, then of course there is no benefit of they're just orthogonal operations. That's what this degrees of freedom region is actually shows. Okay. Um, if you do have an overlap, what it means is that certain scatterers which you are using actually are part of the imaging scene, but also part of the communication channel. Then the illumination from communication actually is providing extra illumination on this overlap part, and that allows us to get a boost on the y-axis, which relates to the amount of overlap between the imaging scene and the communication channels. Okay, um, and that's why we actually have, compared to the no overlap case, which is a blue square, we get a boost in the imaging degrees of freedom. Okay, um, and in fact, can we actually get that? So there is a very simple scheme which can actually achieve some of these gains, which we call decode and imaging. Um, so the idea is that first, the transmitter actually sends pilots. At the base station, we will estimate the channel which we need for communication purposes, but we'll also estimate the reflectivities of the overlap region, which is this little small egg-shaped thing which is at the bottom of the imaging scene. Once we have done that, we can actually start sending data on the uplink and also turn on the blue, which is the imaging signals, which allows us to, at the base station, to both decode uplink data because we already know the channel estimate, and but also estimate the reflectivity using both the illumination from the base station and the mobile nodes. And this scheme, what we call decode and imaging. You decode the data first, then you use the decoded data as additional illumination for imaging. Okay. And if you look at how much decode and you can actually see that the outer bound, which is this outer pentagon, and then the inner bound is the decode and imaging pentagon, you actually get a significant gain. You actually get part of the very close to the outer bound in certain cases. You overlap with that. Okay. Only on the x-axis they don't overlap. And the reason is that the outer bound is actually derived with using coherent capacity. That means it assumes the channels are known. In practice, they are not known, and that's what decode and imaging is doing through its pilot scheme, which is the first phase. So it's losing some resources there, and that loss is what shows up as the difference on the x-axis. As a result, um, in this case, we actually know that the outer bound is loose. So we are not surprised that we actually cannot achieve it. Um, However, what you see is that even in a practical case, what we call opportunistic gains are possible. That means communication is going on, we're losing no data rate from it, but that communication allows us to get some imaging gain. Okay, so that's very interesting aspect of this bound, no, this method. And then when we actually are willing to take some rate hit, we can get the maximum degrees of freedom possible for imaging using decode and imaging. Okay, so that's why this the achievable decode imaging actually matches the outer bound. So it's an optimal scheme for that part of the curve. Okay, so you can compare with time sharing. The time sharing is you have parts of time devoted only to imaging and the other parts only devoted to communication. You will get a curve or area shown in this particular thing on the right. And if you compare it with the rest of the curve, you see a significant gain in terms of um, degrees of freedom when you actually do decode and imaging, okay, compared to just time sharing. Um, and this time sharing idea is somehow similar to what is being discussed in the literature in wireless sensing, where there is a significant focus on um, essentially using signals just only for sensing purposes. And it's but now we're showing you that if you actually do both operations simultaneously, sometimes both of them can benefit from it each other. Okay, now here is a very special case, which is what which will happen in practice. You have many mobile nodes scattered in the city. They are all illuminating by the scene because they are illuminating it from different parts of the different angles. So in a sense, everything on the middle, all the scatters are being illuminated by potentially different mobile nodes. So in practice, we will see a lot of overlap or complete overlap between the communication channels and the imaging scenes. And in this case, we actually can show that the decode and imaging is an optimal scheme, especially if the aperture sizes are all equivalent. Okay. Um, and there is this very special case, which is actually even more interesting. Imagine the base station didn't care about actually sending any data, and all it was wanted to use is you're sending data. It is bouncing off different objects in the scene, the walls and the cars and the people. You use all those reflections at the receiver to actually not just estimate the data but also do imaging. And what you can show is that decode and achieving again achieves most of the upper bound, and there is actual gain. You can actually do imaging, what we call opportunistic imaging, by just leveraging ongoing communication. So it's like in the Batman movie, you're actually sending all these signals, and the original purpose is not imaging, but you can actually use it for opportunistic imaging as much as based on how much of the scene is being illuminated. Okay, so that leads to a very interesting situation, which could be that the in the wireless networks, one can imagine that ongoing this functionality of imaging could be simply layered on today without having to do anything extra, without having to send any new signals. So I think that's a very exciting possibility for network carriers to consider uh, adding these new functionalities. Okay. Um, so actually, I that's all the remarks I had. I know I actually kind of went through it fast, so I'm hoping there'll be Q&A and leaving enough time for the next talks. Um, so the takeaway is that the uplink signals can be very useful for imaging, only with small amount of data, with small amount at smaller rates. Um, Key message I want to say is that there is a unified metric which is actually possible to study this up together, and that actually opens up nice doors for analysis. Um, it is an infinite SNR metric, which we already know are the limitation of degrees of freedom. So our ongoing research is to study finite SNR trade-offs using these stochastic definitions of resolution, other system configurations to study. Right now, we have a very simple idea of only one transmitter and one base station. Clearly, that's not how things will be. We want to study scaling effects. If you have many nodes, then what do you do? And then the key thing we are working these days is on experimental demonstration of these ideas. Um, we actually have a new platform, which is a base stations, which are completely operational, have nearly 100 antennas. They're deployed on our stadium, and now we have multiple such base stations. So we are actually working on building a demonstrator for large scale imaging these days. And once we get through that, I think then it will open up the whole possibility of actually developing network protocols for these multifunction networks. So um, full duplex is going to play a role for us sensing the environment. So these radar-like functionality, which will be really crucial, which is the radar is essentially a time of flight imager in some, and the possibilities of actually doing that are just endless. Already the community has demonstrated many such great ideas of sensing humans, sensing gestures, objects, tags, providing contextual information of the environment. Um, and so really very exciting times are there. I think all these different ideas are merging together, the communication ideas on full duplex and all these other ideas of using things for sensing. um, and I think imaging could be that abstraction which is provided in the networks, which allow many new functions or apps or sensing apps to be built on top of it. Okay. So with that, I will stop. And I think I left a lot of time for questions, and I'm hoping there'll be some discussions and some ideas, um, and looking forward to people's reactions.
Right. Thank you so much, Ashu, for the great talk. Questions from the audience?
Hi, Ashutosh, Rajiv here. Great talk. Thanks so much. I was just curious to know. I have two quick questions. One is that I was just kind of thinking, how will this approach work? How effective is this approach in a very dynamic environment? Right, when you have a large number of objects and there's high mobility there, what do you think will be the performance? And the other thing I was curious was, you know, there seems to be a lot of limitations because reflectivity is your key metric, right?
Right.
So, can you highlight the limitations of the approach that you have? Thanks.
Yeah. Yeah. So both of you are spot on. I think right now this is very theoretical. So I think practical demonstrators are crucial. So I'll take a stab at it, not based on actual evidence, but mostly based on, I think, I would say, our understanding of imaging in other domains. So what you're asking is really speed of imaging. So imaging is, we will be basically doing videos. You can think of it that way. So that means what frame rates we can actually operate at, and are those frame rates sufficient to capture practical mobility in this environment? Um, and I think that will depend on in what is the bandwidth available and at what speed actually these things can be built. So in my opinion, I think um, the limitations will be largely resolution rather than the mobility or the because the resolution is going to be very poor in these systems, and that's because we just have very few pixels. Even 100 pixels are not enough. um, but we will actually be able to, I think, track mobility fast enough just because we have very coarse resolution. um, um, I think your second question, sorry, I already forgot. What was it, Rajiv?
Yeah, it was about this reflectivity and the limitations in that approach.
Oh, okay. Yeah. Yeah. So well, I'm in the sense that all we are trying to measure, one way of thinking about it is whether there is an object or not and how reflective that object is. That is just one way of modeling an imaging scene, and it's a very common way of modeling imaging scene. So if you think about, when you actually look at RGB images, they are actually all essentially reflecting, measuring reflectivity at different wavelengths, which is red, green, and blue wavelength, right? So that's basically what a camera is. It combines the amount of reflected energy for each of them, and that's how you get color, for example, right? So color is just different wavelengths. Uh, but that is what they're actually all measuring, reflectivity. Um, so in that sense, it is just a model which is already used and which we are familiar with. Um, Now, the question, I think maybe what you're trying to get at is that how useful it is at the band, let's say at 6 gigahertz band or at millimeter wave or things like that. And millimeter wave and higher band, 100 gigahertz, this model already is proven to be useful. If you look at, currently we use millimeter wave actually mostly for imaging. Communication use is relatively new. So when you go to airport, your airport scanners where you kind of raise your hands and it goes scans around it is operating at a millimeter wave, and it is measuring reflectivities, and it uses those reflectivities to actually understand whether there is certain type of material or not. Let's say a weapon or not, right? Similarly, car radars are all uh, millimeter wave. So already we used um, these wavelengths for imaging purposes. That's mostly time of flight imaging, or some of it is material properties. But in terms of model, I don't think it's that deficient. Um, the reflectivity model. Um, I'm not sure whether I answered your question sufficiently
Yeah,
clearly
thank
or
you.
not.
Thank you.
Yeah, yeah.
Hi, sure. This is Manisha. Great talk. So, actually, building on what you just said about millimeter wave. So, clearly, one of the things that maybe I missed in the analysis you presented was how does bandwidth factor into it? So,
Right, right.
one of the biggest gains of going up to millimeter wave is you can have much higher bandwidth. But on the other hand, I think the difference between communications and imaging would probably grow in millimeter wave, because when you're doing communications, you're really trying to get narrow beams pointed at each other, at transmitter and receiver, whereas for imaging, you actually don't want that. You probably want much more of a wider beams at both ends. The second question I had was that, so clearly what you're doing is really exciting, but it's not going to compare with actual images. So have you thought about what are the unique applications that you could enable by doing this, especially in the lower frequencies that I think you're focusing on?
Right. So I think maybe I'll take the second question first, and then I'll go to the first one. So I think when we say imaging, our first kind of view is images we see from our cameras, right? And we can't do that. Our resolution of anything is limited by wavelength. So if the wavelength is larger, that's the size of features we can see. Um, so if the wavelengths are millimeter wave, you'll see millimeter wave as our resolution. If it's uh, sub, sub 6 gigahertz, it'll be in centimeter resolution. That's just the limitation of that's physics limitation. Um, so the so I think there is a lot of exciting things one can see. They don't need to be human interpretable. They can be machine interpretable, but they can be a lot of exciting things you can see. So, for example, uh, at lower bands is mostly specular reflection, so they essentially operate like radar. So if you have cars, they get one reflection per car. You can use it for car counting. That means traffic counting. Base stations can be doing traffic analysis. Um, and if you actually look at millimeter wave, you can actually then do human contours and stuff depending on the distances. A very good application is finding people in burning buildings, basically, where light becomes useless, but now we still have penetration of wireless. So imagine everything around you just switching on into imaging mode in emergency services, finding people in these scenarios. So these are just two, applications. But the moment we have this capability, I think people are going to think of a lot more applications. Now, the first question was, your point was that millimeter wave you want to be pointed for communication and actually, and for imaging you don't need to be. Actually, that's not really true for imaging. A lot of imaging works in a raster scan mode, radar being one example. You actually use very pointy beams to raster scan. You just do it really fast, and as a result you can get a pretty good time of flight imaging. That's how most time of flight imagers work. So imaging is by itself such a broad area, and then ways in imaging happens is very, very large ways away. So there are some we are used to, which is ambient light imaging, which is our phone cameras, but that's only one of the many ways imaging happens. So I think there are actually benefits of actually having narrow beams for imaging also, because you can get actually time of flight information much more accurately. And lastly, I think you made a comment about bandwidth. Bandwidth is really crucial. Bandwidth provides direct distance resolution, and that provides depth resolution. So your depth resolution is dependent on how large your bandwidth is. So millimeter wave gain or higher bands are going to be very, very good for those kind of situations when you can get better depth resolution. Monisha, did I touch upon all your questions?
Yes, you did. Thanks.
Thanks.
Hello, Ashutosh, Anurag here. I came into your talk a bit late, so I understand from the answers you've given to others that by imaging you actually mean imaging. That is, you want to make an image of the scene.
Right.
Now, in an indoor setting, I think the ideas that you presented, I think would also be used to cooperatively get a propagation model for the building. So rather than every base station and every pair of nodes estimate a channel between them, can n nodes cooperatively not estimate the channel so that the n plus first pair of nodes can get a better channel estimate?
Yeah, and actually, it's a very intriguing idea, and we are going in circles on this idea. If I understood your idea was to use this imaging to improve communication, and I think you're suggesting one way of doing that by eliminating channel estimation for some of the next node, if possible, or reducing that overhead. But this whole idea that somehow, if I knew something about the environment, let's say I gave you 3D Google Maps, could you actually reduce or improve communication? And it just feels like there's something there. And I think I guess so I think all of our gut feeling is probably well aligned, but we haven't actually come up with a good way of demonstrating it. So it'll be great if somebody can come up with a way of saying, here is a scenario where extra contextual information actually can, whether we get it from imaging or we get it from maps or something, can actually improve communication spectral efficiency. And I think that'll be great. If somebody can open the door on that one idea, it'll be fantastic.
Okay, thank you very much. I think
Yeah,
you answered
thanks.
my question.
Very nice talk, Professor. Thank you. So I was thinking when you scale up the system, the communication part, I mean, it's relevant to a particular user equipment. But the imaging part, it can be shared among multiple user equipments
Right,
as well. So
right.
maybe we can, share data and actually improve upon the imaging. So I wanted to know your thoughts on that.
Yeah, yeah, absolutely. And that scaling in imaging is actually very good, happen in many ways. So in fact, more users talking is actually good for imaging. And so the way a visual picture or conceptual picture I have in mind is a way to think about um, illumination in wireless system is like fireflies. You have all these mobile nodes which are sending data. Let's say consider uplink scenario. So they are scheduled, or they are going on and off very fast pace. It's like fireflies. They're just going around, and you have small amount of light being sent or illumination signal being sent as they communicate, and as a result they're just illuminating different parts of the scene. So in this case, the more of them is actually better for imaging. So it actually, while it is not necessarily good for communication, it's actually very good for illumination, for imaging. And in fact, there are some theoretically you can actually show it too, that this scaling is actually good for them. I think what you're pointing out is additional way that if some people are already doing it on my behalf, or surrounding ways, kind of similar idea as Anurag mentioned. If there are already several people doing it, perhaps I can leverage what they already know to do better job. And I think that's idea. I think has a very strong, definitely will work out. I think it's just a matter of one of us working it out, but I think it will work out. That definitely we can learn from each other and use each other's estimates of reflectivities, for example.
Uh, Thanks, Professor Ashu, for agreeing to give the talk. Very interesting one. This is Gary Mundy from Qualcomm. Um, when you said in the diagrams you showed earlier, it starts to look a little, particularly on the receiver side, it starts to look a little like a traditional multi-user detection problem.
Right.
But I think you probably looked into the existing receiver techniques like SIC and such, and they're probably not suitable for for the application here, where you're actually trying to separate out communicate a desired communication signal from a desired imaging signal. Can you comment on where or why traditional receiver algorithms would not be suitable for this kind of problem?
Yeah, so I don't think I have any thoughts on whether whether they will work or not. I have a feeling they would. The only difference might be that they need a little bit of an adaptation. Um, so in this decode and imaging scheme, actually, kind of this is only one of the schemes which is an achievable scheme, which is optimal in some cases. So I think there are other variations of this idea, but here decoding, which is essentially finding one out of many code words, known code words, right? Reflectivity is an estimation problem, which is that I have some continuous numbers which I want to estimate. So I think a turbo architecture or a iterative architecture will definitely be useful, but they will be now iterating between improving estimates of the bits and improving estimates of the reflectivities. But um, that actually has been also investigated from improving channel estimates and and decoded bits in an iterative manner. So I think those architectures will apply here, because in some sense, estimating reflectivity is kind of like estimating a channel. It's just that it is decoupling the channel matrix into three parts, with the path loss, or the path delays, reflectivities, and path delays. But I think many of those architectures will apply, in my opinion. So I think you're spot on that practical systems will rely on those architectures. This is mostly a more info theory analysis, so it doesn't really actually get into some of these details.
Hello, Ashutosh. This is Ayon from IIT Madras. So my question is, so the accuracy of these imaging systems, right? This also, how do you think is related to the a parallel positioning ecosystem of the transceivers? Because if you do not know the location of the transceivers quite accurately, maybe it doesn't
Yeah.
meet the purpose of using millimeter waves, right? So we need a parallel kind of an infrastructure-free approach to also evolve positioning infrastructure, right? And how
Yeah.
critical is it for like joint imaging? That is the question.
Oh, wow. This is like a really important question. I mean, all questions have been really good, just spot on. So this is another one of those really important questions. So, um, and in fact, you're pointing to an important assumption I made without ever saying it. I
Yeah.
said all these path delays are known. All I need to know is reflectivities, and knowing path delays is essentially knowing location. Um, so, um, but turns out, so while it's really important for doing this analysis, I think if we actually had a good geolocation infrastructure, so base station location is known, but the mobile one is important, then whatever I said applies. However, if we is going to assume that that's never going to be perfect, there'll be always errors. I think the next set of analysis has to be, um, hey, how do we build robust imaging when we know there are location uncertainties? Okay, and what are the methods? And I think that's like going to be a nice area to research on. Our early results, we actually have a mechanism of just jointly estimating. We have some coarse estimate of location, and then jointly defining, kind of like what Giri was saying, that kind of refining estimates. And the way we do that is realize that some of these nodes are moving. In fact, mobility can be used as a mechanism for improving your estimates. So you get actually many estimates. If you assume smooth mobility, you actually get additional set of equations. But you're right. I implicitly made an assumption about location is not going to be true, but I think it is not a deal breaker yet, because I think there are mechanisms of dealing with that uncertainty, much like what we do for a lot of communication system where we do not know many parameters, but we estimate them.
Because one of the use cases you mentioned is like disaster or public safety kind of scenarios, right? Where we need imaging, and there we do not have infrastructure for doing like accurate positioning, right? And
Right, right.
so yeah.
I think I have a feeling that if we find value in this thing as a community, we're going to address all these difficult parts of it. Um, And so I think each of these questions is like a good research question. Some of them are bigger than others, but I'm kind of glad that people ask these questions, because those are all the things we are thinking about these days and working on. So, so it's some of them we don't have answers. Some of them we have some good ideas on how to approach them.
Thank you, Professor.
Yeah.
Uh, Hello, Ashutosh. Very nice talk. This is Mukulika from Triple IT Delhi. So, you mentioned about the fact that Wi-Fi sensing and networking coexistence has some similarity with imaging and networking. So, could you elaborate on that and how this imaging and networking is different from sensing plus networking?
Right, right. Yeah, I think that's really important. And so the way to think of sensing, at least the way I think of sensing, is most of the pretty much all the literature is that you choose a property of the scene to estimate. And this property of the scene, for example, could be a gesture of a human. And then that's the only thing which is a signal. Everything else is unimportant or noise. Um, so, so here are strong, great examples of very, very nice piece of work. Um, like estimating heart rate or gestures of people or how many people are in the crowd. So you're saying here is a scene. In this scene, there are certain things I care about, and I will only going to want to sense those parts of the scene, and that's what I would call sensing. They have certain objectives. Imaging actually does not try to interpret the scene. It just says, here is some scene. This scene has objects. All of them have some reflectivities and some distance. I just want to know what they are. But whether that object is a person or a box or a table, or does it has a heartbeat or not have a heartbeat or anything, is not relevant for imaging, right? So imaging is essentially decoupled from interpretation or any particular parameter. And that's basically the key difference between the two. And personally, I think the reason for studying, at least my reason for studying, is what is the layering architecture we would need, because we are not going to build networks or network protocols which will sense parameter A, parameter B, parameter C, because that's just, I think, too limiting. The reason why our layered architectures work is we don't actually try to interpret data. We just send bits no matter what they are. So I think the equivalent, at least my current thesis is, the equivalent is we just try to estimate whatever the scene is, but not try to interpret it at lower layers, and let apps or things on the higher layer extract parameters. That means the sensing things should be apps built on top of imaging. And while that may not be the most efficient architecture, is likely going to be the most useful architecture. Where and that's partly the motivation for studying imaging. So I hope I answered the two questions, one you asked and one you didn't ask, which is why, what's the difference between sensing and imaging, and kind of why we are focusing on imaging potentially as a lower layer construct to build all sensing upon, which may be a good layering approach.
Yeah, thanks.
Hello, sir. So my question is related to the trade-off itself, like how you have shown regarding the overlapping and non-overlapping. So if we consider the quality of the image and the user-specific parameters, be it like as you said, it is in the uplink domain. So like the kind of like should it be directional or the waveform? Like what should be the trade-off between these and the quality of the image? Like how will it affect the user-specific parameters in the uplink? Like,
I think so. Let me take a crack at the questions and see whether I understood correctly. Whether I think maybe your question relates to what type of signaling one must use
yes, yes.
and how that signaling impacts, right? So that actually this analysis doesn't necessarily answer that question. It does actually doesn't address that question. It just shows that if I choose to only dedicate the uplink signals for communications, but not necessarily worry about designing them, like whatever. So here the assumption is I will use the best signal for that purpose, but I'm not actually giving the structure of that signal. But you're asking a really important question. Okay, I'm convinced I should do it. How should I design these uplink signals? Should I make them directional or not? Should I change the waveforms or not? that this analysis does not answer that question, because that's actually not, it essentially implicitly assuming that I will choose the best possible, but without specifying what that best possible is.
Okay. Yes.
Yeah, and that's one of the limitation of the whole degrees of freedom framework. It's actually
See, if
not
we
necessarily
consider
sometimes good for design.
if we
Yeah,
consider the interfering thing, which Rajesh sir also asked a similar question, like in the coming future, like we are hearing about the IRS also, intelligent reflecting
right.
surfaces and all. So will it be a boon or a bane? Like we are having more reflecting surfaces and all. Like can you use this also, like IRS also?
I think if they are controllable, so this is actually, just think about it, is that when you go to a studio and take a picture, actually there are reflective surfaces used to put enough light on you so that this light illuminates you from all sides, and that's how we get good studio pictures, right? And that's our reflective surfaces. Mm. Now, in that sense, we kind of know that this is a subject, which is, let's say, I going to a studio and we need to illuminate Ashu's face to take a good picture of him, and hence I should align surfaces around it so that I get the good illumination and get a good picture, right? So in this case, we know it is absolutely very useful to have it. Um, Now, if we extend this idea further and we say we have these reflective surfaces which we control, we can turn them on and off, we can change their angle and reflectivity, and then we want specific things to images. So here's the example would be a building is on fire. Now the fire department actually comes with reflective surfaces and directs a lot more energy towards the building so that all sides of the buildings are now illuminated through wireless signals, then so that we can make sure that every part of this building interior actually gets some energy and then reflection out. In that case, one can imagine reflective surfaces will be a boon. Uh, but I think so. We may have to probably dive deeper into actual cases to answer that question. But I think knowing what we know about visible light imaging and how we use them, I can just see direct analogies. They will be extremely useful in other wavelengths, other bands.
Thank you, sir.
All right. Thank you so much, Ashu, for the amazing talk. And also, we had so many questions and time for so many questions. So that's also wonderful. So once again, let's give a very big round of applause to thank Professor Ashutosh
Thank you,
Sabharwal.
thank you. Much appreciated.
We have a packed audience here for you too. All
Yeah,
right. Thank you so much, Ashu, once again. And we hope to see you again at future COMSNETs. I
absolutely.
hope you in person too.
Yeah,
All right. Thank you so much.
absolutely. Yeah. Thank you all. Much appreciated.
All right. So for everyone else here, we have a back-to-back keynote right after this. So we'll take a brief 2-minute pause as